Today we're going to take a look at some more dilations, check out some angle properties, see what happens when they're from different centers, and then start to make some connections with the transformations and dilations. So one big huge thing with dilations is that dilations are angle preserving, meaning they do not change. Angles will stay the same size when they are dilated. So we can see here dilations map angles onto angles of equal measure. Now, if we were to look at polygons, so some sort of a shape, if I had dilations, it says it maps polygonal figures to polygonal figures whose angles are equal in measure to the corresponding angles of the original figure, and the sides whose side lengths are equal to the corresponding side lengths multiplied by the scale factor. So a different way to say that is that the sides are in proportion. Oh, I can't spell today. So keeping that in mind, we have a triangle. It says triangle DEF is dilated by a scale factor of 5. Which of the following statements would be true? Well, we're looking at angles here, and if I'm looking at the angles, they're telling me angles are going to change. We know that these can't be true because we just learned that angles are going to remain the same or stay equal in measure with the dilation. So now I have to think, okay, what is going to be changing here? Maybe a good idea to draw a picture just to kind of see what's going on. Seeing your scale factor is 5 means this picture would be getting larger. So if I were to draw out a larger triangle, and now take a look at what we have remaining. So I either have DE is equal to only 1/5 the size of D prime E prime. That looks good, but check out your last one. EF, it says, is equal to 5 of these. Okay, that doesn't look so good. So our answer here has got to be choice 2. So what happens if our center is not at the origin? Okay, well, we're going to use this process. We're going to do a dilation of 2. Center of dilation is T. So we're starting here. That's your center. It says we're going to find the slope from the center of the dilation to the new point. So if I'm looking at this thinking slope, I'm going to be going up 2, and if I count over, I'm going to be going over 5. It says repeat that slope according to the scale factor. So that means I have to do that slope twice. First slope is the slope we count into the point, so that's already 1. Then I have to do it again. So I'm going to go up 2, and I'm going to go over 5. And that would bring me right to that point. So now this is H prime. And if I'm looking at H prime, that's going to turn out to be 7, 8. And the third piece of information, it says don't simplify the slope because it's actually representing the vector. So back when we did translations, we talked about vectors being that directed line segment has both direction and magnitude. So I don't want to reduce those. Okay. Same idea here. It's just what happens if I have a fractional dilation. Okay, works the same way. So step number 1, our center is going to be at T, and we want to find the slope from the center to the new point, keeping in mind we are not reducing. So it looks like I would first be going up about 8, and then I'd be going back, or think like negative 12. Okay, so if that's our slope is represented by change in y over change in x. So our change in y, should be our 8, and our change in our x value is negative 12. So what that's saying is I only want 1/4 of this. So I'm going to repeat the slope, but only do it according to the scale factor. I want 1/4 of the change in x, 1/4 of the change in y. So 1/4 of 8 is 2, and 1/4 of negative 12 is negative 3. Okay, so if I try this again, I'm going to go up, it looks like 2 units, 1, 2, and then I'm going to go over to the left 3 units, so 1, 2, 3, and here's my new G prime. So if we were to find the coordinates for that, the coordinates turn out to be at 5, 3. So a couple more dilations. So what if the dilation has the center of dilation is at the vertex? Okay, well, we do the same thing that we would have done if it was at the origin, or like what we did before, we're just going to think of it as like the slope again, and just do it however many times the scale factor says. So the center of dilation is at C, and we have a dilation scale factor of 2. So if I think slope, so to get to B, I have to go up 1, and I have to go over 2, so I'm going to do it again. Up 1, over 2, here's my new B prime. Okay, center of dilation is C, count it again for A. So I have to go up 3, back to the left 1 to get to A, so I go up 3, back to the left 1 more to get to A prime. So if I were to trace this out, I could see here in red is my new triangle, scale factor of 2, so it should have gotten larger. Okay, what if it's inside the shape? Same thing. You're going to count using slope starting from the center, count to the point, and repeat it for the number of times your scale factor tells you to, in this case 3. So if we start at A, I have a slope that goes up 1, back 1, that's 1. I have to do that 3 times. Up 1, back 1, that's 2. Up 1, back 1, that's 3. Here's my A prime. Okay, C is nice and easy. Counting down 2, that's 1. Count down 2 more, that's 2. Count down 2 more, there's 3. Okay, same thing with B. I'm counting over 3, that's 1. Now this one's going to go off the grid, so I apologize. Over 3, that's 2. Over 3, that's 3. And there's my B prime. So again, if we were to connect this, scale factor is larger than 1. I should see it getting bigger, and it does. And it grows, I can see, around that center. Okay. If it's outside the shape and I have a scale factor of 1/2, so this is kind of similar to what we did before. Find the slope, and then we're going to go back and only do about half of it. So if I'm looking at, let's maybe start with G to A. So it looks like I'm going to go down 2, and then to the right 1, 2, 3, 4, 5, 6, 7, 8. So if I'm thinking maybe from G to A, I have to go down 2 and to the right 8. Now I have a scale factor of 1/2, so that means I only want to do half of each of those. So half of -2 is a -1, half of 8 is a +4. So what does that mean? That means I'm going to go down 1, right 4, and here's my new A prime. If we look at B, B is going to be another big one. So from G to B, let's count your slope. So I have to go down, it looks like 1, 2, 3, 4, 5, 6, 7, 8. And then I have to go to the right 1, 2, 3, 4. So I have a slope down 8, right 4. And now again, scale factor is a half, so I only want half of each of these. So half of -8 gets me a -4. Half of 4 is going to get me 2. Okay, so we go back starting at G, and I do that again. So I want to go down 4. And I'm going to go to the right now, 2, 1, 2, and I can see right here is going to be where B is located. Okay. C is a little bit easier. C, I just have to go down 3, and I only have to go half of 3. So half of 3 is 1/2, so I'm going down 1.5, and here's my C. Connect the dots again. Scale factor being 1/2, I should see it getting smaller, and I should see it moving closer to the center, which I do. Okay, what if I have the dilation and I have to determine the center? Well, we could do this a couple of ways. 1, you could think slope. 2, you could actually just connect your straight lines. So if we think about this in terms of slope, which will also help with our scale factor, I want to see starting at my transformed point, moving towards the original point. So if I count, I'm going down 2 to the left 1. That was 1 transformation, so I probably have to do it again. Down 2 to the left 1. I'm going to put a point right there. I'm going to try that with A and see, does that remain the same? So I'm going to go down 1, left 1, 2, 3, 4. So I'm going to try it again. Go down 1, left 1, 2, 3, 4. And it looks like we have found our center of dilation. Okay, so our center is going to be located at -2, +1. And again, like I said, you could also do this by connecting the points. So if you took a straight edge and you connected it, a straight edge and you connected it, you're going to see all of these are going to intersect still right at that center point. Now your scale factor, again, it's saying, well, how many times did you have to think slope? Well, we did it once, twice, so that gives us a scale factor of 2. Okay, so everything that we've done has been based off of dilations. And what we get, dilations will produce a similarity transformation. All of these shapes that we have done with dilations are similar. We said sides in proportion, angles are equal. So we can also just say a similarity. And it's a composition of a finite number, meaning countable, of dilations or basic rigid motions. So the scale factor of a similarity of transformations, if I have more than one dilation, well, all I have to do is take up the scale factors, multiply them together, and that would get me the total dilation scale factor for the composition. If there's no dilations, then the scale factor is 1, and if there's no dilation scale factor 1, then it actually means it's a congruency transformation. So we can say geometric figures are similar. Notice our symbol, we get this little squiggle. If all pairs of corresponding sides are in proportion and the angles are equal, and that's what we've been saying all right along with our dilations. Okay, so if we were to look at this over here, it says define the transformation that would map the pre-image on the left. So here's our pre-image, here's our image, and we want to see what would happen. Well, to go there from the pre-image to the image, I know it has to be at least a dilation. And I could tell you, because it's getting smaller, I know my scale factor has to be between 0 and 1. And then what do we know about these figures? Well, since a dilation has happened, I can tell you that they must be similar. And I'm going to use my symbol, so they are similar. And so what does that mean? That means the sides are in proportion. And then that means that the angles are congruent. And when we're saying sides in proportion and angles are congruent, what the one big thing we have to keep in mind is these are our corresponding sides. Oops. Corresponding. Same thing with angles. These are our corresponding angles, meaning the parts that match up. Okay. Going down here, taking a look. Figure 1 is similar to figure 2. So which transformations compose that maps figure 1 onto figure 2? All right, well, if we take this step at a time, if I'm starting at figure 1 and I'm going to what's labeled as R1, I could definitely see a dilation had to happen. And because it got larger, I could tell you that our scale factor had to be greater than 1. And then to get from that R1 location to figure 2, we had to have some sort of a reflection. I can see that orientation has changed. And maybe what I would do here is draw on a line, label that line, and I could say a reflection over line. Okay, and our last one here. So we have given that triangle ABC and DEF are similar with congruent angles. It says give a similarity transformation that would take ABC onto DEF. So this is kind of like your pre-image and this is your image. So we could do this a whole bunch of different ways. I'm going to start with triangle ABC and I'm going to say, how about we rotate it? I'm going to say centered at B. And it looks like we're going about clockwise 90 degrees. Okay, so then if I do that, well, now I have to shift it. So I'm going to say from there, I'm going to translate. So I'm going to translate so that my angle B, when I'm done, maps onto angle E. Okay, so I rotated it, now I've translated it so B and E match up, but now I see that ABC is a little bit smaller, so now I need to do a dilation. I need my center, so it looks like center's got to be at E since B and E were together. And now I need a scale factor. Okay, so this scale factor, I don't have any numbers, and this may be a little difficult to figure out, but let's think about this. So I know whatever the length of AB is, AB had to be multiplied by something to get me that length of DE. So if I don't know what that something is, that K value, if I divide through, let's just say by AB, what I get, while it's not a number, is I get a scale factor using variables. So I could tell you my scale factor in this case is going to be the ratio of DE compared to AB. So that would be how you could determine a scale factor if no numbers are provided. Now, that's not the only transformation that you could do it or the only order. That's just one option. So I hope this helped. We'll practice some more in class, and don't forget to like and subscribe. Have a great day.